Hello, this is section 3.1 for Calc survey, and today we'll be talking about derivative formulas for powers and polynomials. So finally, we've spent chapter 2 discovering, the slope of the tangent line and sketching derivative graphs, and finally we get to learn how to actually find the formulas for some of these derivatives, the really basic ones. So just a refresher, you've got your function here. And if you want to sketch the derivative, remember the derivative represents the slopes of your tangent lines. And you can see you start off pretty steep and it's positive. And as you approach this maximum here, you start to level off. And that's representing here. You've got positive slopes that are getting smaller because you're leveling off. And then once you hit that slope of 0 where it crosses the x-axis, then your slopes are steep. Now you have negative slopes that start off flat and get steeper, then somewhere in here is the steepest, and then it starts to flatten out again. So that's what's happening here. And then the same thing happens when it's now increasing and your slopes are positive. Okay. Then to graph the second derivative, we just use the derivative graph, and we see that all those slopes are negative till we get a slope of 0, and then all these slopes are positive. And then remember, we also talked about on your double derivative, this is also going to tell you where the original function is concave up and concave down. So where the double derivative is negative, you can come over here and see that your original function is concave down. Where your double derivative is positive, your original function is concave up. So those are the relationships we talked about in chapter 2. So let's finally do some derivative rules and get some shortcuts to these derivatives. So whenever you have a function that's a constant, meaning it's a horizontal line, when you take that derivative, well, what is the slope of the tangent line anywhere along that horizontal line? It's going to be 0. So anytime you have a number and you find the derivative of that number, it is always 0 because the slope of the tangent line is always 0. When you have a line, mx plus b, well, along a line, the slope of the tangent line is going to be one and the same. So the derivative of a line is going to just be the slope. A constant multiple, so this is saying if you have a scalar, it does not affect the derivative of your function. You just multiply the same scalar to the derivative. When you add and subtract functions, you do the derivative of each one. And then lastly, here's the big one, the power rule. So f of x equals x to the n. To do this derivative, you're going to pull the exponent down in front and then subtract 1 from the exponent. And you've probably already noticed this. Whenever we had a polynomial function, this would be a degree 3, potentially. Notice it when we did the derivative, it went to a degree 2, and then it went to a degree 1. Oh, so we're subtracting a degree when we do the derivative of power functions. That makes sense. Okay, so here are some derivatives that we can now do pretty quickly. So when we want the derivative of a number, it's just 0. Here's that power function. So you're going to pull the exponent down in front and subtract 1 from the exponent, and that's your derivative. That's amazing. This is your original function. Up till now, we've just been sketching, and we did a couple where we tried to find the pattern to come up with a derivative, but now we just have a simple pull the exponent down in front, subtract 1, and that's now your derivative. If you plug a number in for x, let's say you plug in 2. 2 squared is 4 times 3 is 12. 12 is the slope of the tangent line at 2 on this curve. And now we have a formula that we can just plug any x value we want, and this will spit out the slope of the tangent line. So much nicer, much easier. Now this, if you have a scalar in front, you pull the 4 down and multiply it by 2, getting that 8, and then subtract 1 from your exponent. This is a linear equation, so it's just the slope. That's your derivative. Now, I didn't point this out, but notice every time I do the derivative, I immediately label f prime of x, or if it's y, you can write y prime or dy dx. Either of those two notations work. But always label when you do the derivative. Okay? Now, here's where they get a little more interesting. Now, remember, you only know x to the n. And right now, that's not what I see here. This is not in the denominator, so you've got to move that x cubed up into the numerator and get it into this format. And if you have a number in front, that's fine, but you need to get x to a number. So that's what we do. We move the x cubed up, make it 5 halves x to the -3. Then you're ready to do the power rule. Okay. A very common mistake is students like to pull the 2 up as they pull up x to the 3rd. And why? Leave 2 where it is. If you pull that 2 up into the numerator, you have to make it 2 to the -1, and that doesn't help you in any way. So just move x cubed up, make it x to the -3. Then you can pull the exponent down in front, multiply, and subtract 1. And there's your derivative. Radicals, rewrite it as rational exponents, then do the power rule. That's what we did here. And here's another case of, okay, you've got to get that x out of the denominator. So we moved it up, and here we had to move up the 3x because it was all raised to the -2. So as we moved it up, it turned positive. But again, you're not ready to do the power rule. You can only use the power rule when it's x raised to a number, and this is 3x raised to a number. But you can easily square the 3 and get 9x squared, but now you can do the power rule with that x squared. This one, 2 terms, so just treat it like 2 separate derivatives. X squared becomes 2x, pull the 2 down, subtract 1 from the exponent, and then the derivative of 4 is just 0. And then these 3 are all, well, at least these 2 are set up beautifully for you to do the power rule with each term. So for this one, pull the -2 down, multiply, subtract 1, x to the -3rd. And in this case, that's a linear function, so it's just 2 is your derivative. And here you get to practice using some fractions. And then this one, you would just rewrite that square root of x to the 1/2, and then you're able to go ahead and do the power rule. Okay. But you need to practice these, and these will become like second nature to you, but you need to practice doing these derivatives. Okay, so what would an application type problem look for these? So the revenue are in millions of dollars for Dairy Queen from 1989 to 1993 can be modeled by this lovely polynomial function here, where t equals 0 represents 1989. All right, find the slope of the graph in 1990 and interpret its meaning. So this is huge. Find the slope at a specific time. You haven't been able to do this without doing some type of estimation. But now you can do the derivative of this function and plug in 1, because we're going from 1989 to 1990. That's huge. We can now find that instantaneous rate of change so much faster because you can now do this derivative. So I did the power rule for all of these. And this, of course, that's a linear, so it's just the 37.97. But that's where this derivative's coming from. And then you can just simply plug 1 into that derivative, and there is your dollars, your $16.06 million per year. And we were able to get that instantaneous rate of change. Okay. All right, find the equation of the tangent line to the graph at 1992. Okay, so again, you need the slope and you need a point. So plug 3 into your derivative to get the slope of our tangent line. Plug 3 into the original function to get our ordered pair. Once you have those 2 things, then you can write your answer. Now, not good on Mrs. Cogswell's part. I should write this as R equals 5.18t plus 279.88. Probably you need to use the proper variables. I need to go back and correct these notes. I used to not care, and now I'm a little more picky. So try to make sure you're using the proper variables for our tangent line there, okay? But that needs to be an R, this needs to be a T. But hey, there's a benefit to watching the video. And we'll talk about that in class. All right, so that's an applications problem for the derivative. And being able to find that instantaneous rate of change is going to be very beneficial. Okay, so here's another one. Let h of t equal this function be the position an object travels in feet after t seconds. So find the average velocity of the object from 1 to 4. That's just slope. That's what we've been doing since the beginning of the school year. And then here comes the calculus. Find the instantaneous velocity at t equals 3. So you can now do the derivative of this very quickly and then simply plug 3 in. And this is how fast that object is going at 3 seconds. That's pretty amazing. And the fact that it's positive means it must be going up still. Remember, velocity shows you direction. Had it been a negative velocity, we could say that's when your object is going down. And that should pop up on this next one. Yeah, see what is the diver's velocity at impact? Well, that's how fast that diver hits the water, and there's that negative representing the fact that the diver's going down. But anyways, at t equals 0, diver jumps from a diving board that's 32 feet high. His position at time t is given by this lovely function. All right, when does the diver hit the water? There is no calculus involved in that, guys. You just set your function equal to 0 and you use that graphing calculator that's sitting on your desk, because usually it won't be able to factor, but you can use your calculator to solve this. And you get t equals 2. We throw out the -1. Okay, so at 2 seconds is when that diver hits the water. When does the diver reach the highest point? Okay, well, you have that lovely -b over 2a formula. So you can -b, -16 over 2 times a. That gives you the time. Then you'll need to plug that back into your function to get the actual height. So at 0.5 is when that diver reaches 36 feet. Again, we haven't done any calculus yet. But then here comes the calculus. What is the diver's velocity at impact? That's that instantaneous rate of change. So find the derivative, which is what we've done. Here's the derivative, because now you can pull the 2 down in front, multiply and subtract 1, and derivative of 16t is just 16. And then plug 2 into that, and you get -48. So negative or decreasing 48 feet per second. And there you go. So these basic, I'm going to eventually call them baby derivatives. These are your baby derivatives. You have got to practice these, though. You've got to do your homework to start building that foundation, because they're going to get a lot more complicated really fast. Not complicated, a lot more fun really fast. And if you don't have the foundation, you're going to be struggling big time. So please do your homework. Email me if you have any questions.